My publication deals with the mercury emissions from two volcanoes, submarine volcanoes from the Tonga Arc. But why volcanic emissions? So we have two types of mercury sources. We have anthropogenic and natural. These natural sources are, for example, volcanic emissions in the land, but also underwater, submarine, and also, for instance, release of mercury from enriched soils. So in the last decades, the mercury community has been working a lot in quantifying the anthropogenic sources, and now I think we have a good number to put on it, but we're still trying to put a number on the natural sources. That's the topic of my research in this moment. And our publication, what we did is we went to the Tonga Arc. This is a chain of volcanoes that are in the Pacific Ocean. And the idea was to collect in the first place just seawater. So we did a transit passing through the Tonga Arc, but also collecting water in the surrounding areas, in the surrounding ocean. So we collect water in the surrounding waters, in the surrounding Pacific Ocean waters, and what we saw is 1 picomole, so seawater, so no problem, everything good. But then we tried to go really into the two volcanoes that the publication is about, and we tried to go really close and take the plume waters, the water that is coming out of these volcanoes. And then the concentration that we measured was more than 4,000 picomole, so a lot more than in the ocean. So we were very excited, so we were thinking, okay, if the water of the plume is so high in mercury, then the organisms that live around the area should be very affected, because mercury is a contaminant. But the problem with when we talk about this hypothesis is that usually we have just few samples. So either we have seawater, either we have plume waters, either we have the phytoplankton or the sediment, but never we have all the things together. So when we saw that the concentrations in the plume were so high, we decided, okay, we will take everything that we can take. So we took sediments, plume waters, phytoplankton, seawater to have the complete picture of what we were seeing. And then we started to analyze. And for our surprise, when we went and analyzed the concentration of the phytoplankton, it was one of the lowest that we have ever measured in the ocean. So where is the mercury in the phytoplankton? So we didn't know, we were not expecting this at all. So we continue analyzing samples and trying to understand what was going on. So in this context, we went and talked with the iron people. So iron is an element that is essential for growing, for the organism to grow. And it's very limited. So there is in the ocean iron, but sometimes the concentrations are so low that the organisms don't have enough iron to grow. So we talked with these people. They also got samples of the plume, of the seawater, and what they saw is that the plume had a lot of iron. So there is a lot of mercury that is coming out, but also iron. So as we had the phytoplankton, we calculated how much phytoplankton was in the plume. And then we realized that there was a lot of phytoplankton that was growing because they have more iron, they have more things to grow. And then what we saw is that as we have so much phytoplankton, this mercury that is coming out, it gets what we call biodiluted. So each one of the cells of the phytoplankton get less and less mercury because they are a lot, so they can share, let's say, the mercury. This is the first time that we see in a hydrothermal vent, in a submarine volcanic vent. This is very interesting because it changed a little bit the way that we see hydrothermal and volcanic sources. So these results are really motivating for the future because we see that little by little we understand more and more the marine volcanoes, but there is still a lot of things that we don't know.